In this video, we're going to tackle some advanced percent abundance calculations. Make sure you watch the introductory video before you jump into these. So in the first couple of problems, we're missing two pieces of information. We're missing the mass of one of our isotopes, and we're missing the percent abundance of one of our isotopes as well. Let's tackle the percent abundance issue first. It's a little bit more straightforward. So because it's a percent, we know that all three values have to sum up to 100%. So in order to calculate the unknown number, I can do 100 minus 92.2 minus 4.67. And when I did that, I got 3.13%. Now, throughout this video, I'm going to mark the sig figs with a little bar on top. So since this value only has one decimal place and it's a subtraction step, I can really only report this value to one decimal place. So I'll make note of that with the little pink bar. The average atomic mass was not given, but since we knew what element we're dealing with, we could look it up on one of the periodic tables. How are we going to set this up? So it's going to look like the setup for the other problems, except for this unknown mass, I'm going to use an x. We're going to be solving for x. You can use any variable that you like. The other thing that I did here is I converted all the percent abundances to decimal values, because remember, in your formula, you're going to plug in the decimal values. Big issue that I see, an error that I often see students make, is they move the decimal place over and they write this as 0.313 when in reality, remember, you're dividing by 100, so you have to move it over 2 spaces. So this decimal value then is going to be 0.0313. I'm going to use the decimal values when I set up my calculation. My average atomic mass is going to be on the left-hand side. Everything's in AMU, so I'm going to leave off the units. Just to save space. We'll tack them back on the end. And then we're going to do the individual mass times its percent abundance written as a decimal. And then we're going to add the second value times its percent abundance and then the third value is just x. So I'm going to do 0.0313x as the third term in my setup here. So let's start simplifying and combining like terms where we can. So my next steps algebraically, I'm going to multiply these, solve, and then I'm going to add this piece to this piece because they're both just values. Let's look at what's going on with our sig figs. So the first step inside the parentheses was multiplication. Here I have 1, 2, 3, 4, 5. I have 6 sig figs. And here I have 3 sig figs. So my result, after I multiply, is going to be cut down to 3 sig figs. So we use that bar again. Remember, we're keeping the whole number till the end of the problem. Just going to mark what's going on. something similar is happening over here. I got, what is it, 6 and then just 3 over there. So I'm going to do 1, 2, 3, and that value would end right there. Leave the other one. Actually, on the other one, I should mark that 1, right? Because we decided that that's where it cut off. Now, when I go to add these two values, I'm looking at something that has 1 decimal place. And this has 2 decimal places. And since they're being added, I need to cut down to the lower number of decimal places. So I'm going to put a bar on top of that value right there. Alrighty, at this point, I still kind of need to combine like terms by bringing the 27.1479 value over. I'm going to subtract it from each side. Alrighty, so after subtracting 28.085 minus 27.1479, kept the whole value, I got 0.937, blah, 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 equals the 0.0313x. I'm trying to isolate the x, so I divided each side by the 0.0313 value. Let's mark the sig figs again. So we're going to the tens place with the 27.1. This value we can consider it all significant because it came from the periodic table. But we're at the tens place now. And so that leaves us on top of the 9. At this point, and it kind of hurts a little bit, right? We went through all this trouble, and now we're down to just 1 sig fig. And we're dividing. The denominator has 2 sig figs. So in reality, our final answer should only be reported to 1 sig fig. So I got 29.939, and there was a higher number, so I would actually round this up. This should go up to a 2 AMU. And I use this value, this mass, to go and check. So I solve it for x, and then I plug this back in, and I make sure that I actually obtain this value. And I used this value, and it worked out. But officially, again, because we're down to 1 sig fig, the best we can do up here is to just say that x equals 30 AMU, which we already kind of knew that, but here's a more precise value, even though all the digits aren't significant. Let's look at the sig figs for this problem and talk about the calculation a little bit. Here we have 4 sig figs. So when we're multiplying, we're definitely cut short by the fact that we only have 4 sig figs in that percent abundance. We can keep up to the tens place after the multiplication. When we subtract, that means we can keep 1 decimal place. So after my subtraction, I could keep up to the 1, the 71.1. Even though I'm going to keep the whole number, just keep it in my calculator as you saw. Then I'm going to divide by 0.3728. All 4 digits there are significant. So we have 3 sig figs divided by 4 sig figs. which means our final answer has 3 sig figs. Now, there's a 9 here, so we're going to round up. And again, very dissatisfying after all of this work. We can report the mass as 191 AMU. If you wanted to keep more digits here, your limiting piece of information is that percent abundance. So we would have to find or determine percent abundance values to more digits if we want to report our mass to more digits using this approach. So in my opinion, numbers 3 and 4 are the coolest of all of the percent abundance calculations. That's because we're going to have to use, in essence, a system of equations to solve for 2 unknown percent abundances. So what I've done here is I've organized the information that they gave us in the word problem. And for my percent abundance, let me arbitrarily mark one of them with a question mark. So I don't know the percent abundance of boron 11. In previous problems, we took advantage of the fact that all of the percent abundances had to add up to 100%. Same thing holds true here. Both of these have to add up to 100%. So I can do 100% minus question mark, and that's going to give me the percent abundance of boron 10. So that's one of the equations that we're going to use to help us solve the problem. Decimal form. So 100% becomes 1 in decimal form. And let me make it more official. I'm going to use y instead of the question mark. So we have y and 1 minus y as our decimals. The setup is going to be the same. We're going to start with our average atomic mass on the left-hand side. And we're going to set that equal to the mass of the first isotope times its percent abundance in decimal form plus the mass of the second isotope times its percent abundance in decimal form Now we can work towards simplifying by distributing this value and getting rid of those parentheses. So I'm going to distribute this to the 1 and to the y. Now I have 10.810 equals 10.013 minus 10.013y, and then I still have this last term. So plus 11.009y. Combining like terms. The second and the third term both have y in them. So I'm going to put them together and rewrite my equation. 10.810, and then we have the 10.013. There's a negative sign here, so that needs to go into my calculator. So I'm going to do negative 10.013 plus 11.009. That left me with 0.996y. Since both of these terms are just flat out values, I can subtract the 10.013 over. That left me with 0.797 equals 0.996y, and we'll divide both sides by 0.996 to get y by itself. And I'm getting y equals 0.8 002, 0. There's a whole bunch of other numbers, but we're not going to need them after we consider the sig figs. So what's going on with our sig figs? Both of these numbers have 5 sig figs. So when I do my distribution step, the 1 is exact, so I can maintain 5 sig figs there and 5 sig figs there. This is a legit 5 sig figs. So 5, and when I do the subtraction, I'm not losing any decimal places. It's kind of nice compared to the previous problems. So at that point, I have 3 sig figs. This is 3 sig figs. 3 sig figs divided by 3 sig figs, and we're looking at 3 sig figs. So y then is 0.800, and then I'm going to do 1 minus y to find the percent abundance of boron 10. And honestly, you should do 1 minus this whole unrounded value. You wind up with 0.200 after sig figs are taken into consideration. To change it into percent abundance, we need to multiply by 100%. And so we can report the percent abundances as 20% and 80%. When I do these problems, they involve quite a bit of work, so I always go back and solve them in the forward direction. So very quickly, I'll plug into my calculator this times this plus this times this, and make sure that I get the average atomic mass out of that set of numbers. And it winds up, for this particular problem, being really, really close once we round and consider sig figs again. Question number 4, we're asked to solve for the missing percent abundance data for this unknown element. Since I didn't know the identity of the element, I couldn't write isotope symbols over here. That's why you see the 1, 2, and 3, just to distinguish between the 3 different isotopes. Just like before, I need to take advantage of the fact that all 3% abundances should add up to 100%. So I'm going to arbitrarily put a question mark in the second line. The question mark could be in the third line or the second line. It doesn't matter. And then I'm going to say, well, these 2 things need to add up to 100%. So my third value should be 100% minus 78.994% minus whatever the question mark value is. I can simplify this. I can do 100% minus 78.994% and rewrite this to be 21.006% minus question mark. Coming over to the decimal side of things, the question mark I'm going to designate as a y, and then I still have to move this decimal place over. So now I'm going to have 0.21006 minus y when I convert my percent abundances to decimal form. Alrighty, so I'm going to start with the average mass. And that's going to equal the mass of isotope 1 times its percent abundance in decimal form plus the mass of isotope 2 times its percent abundance, which is just represented by that y variable. And then we're going to do the third mass, (259) times its percent abundance. I want to get rid of the parentheses, so I'm going to multiply, and then I'm also going to do some distribution over here. So I'll distribute this 25.9 value to both of the things inside the parentheses. At this point, I can simplify even more by combining like terms. So I'm going to take the two terms that are just standalone values, and I'm going to add them together. In addition, I'm going to take the two terms that have the y variable in them and combine them. So the 24.985 value has a positive sign, but I'm going to have to go ahead and subtract the 25.98259 value. Don't miss out on this subtraction sign. Alrighty, so what I want to do right now is work on getting some of my decimal numbers, and then I'll go back and consider the sig figs. So I need to do 0.21006. I'm going to take this value here, and I need to subtract the y value that we just obtained. That gives me 0.11009074. And let me also write down that number. So sig figs. There's 5 sig figs here and 7 sig figs here. So the result is limited to 5 sig figs. Likewise, since I'm combining it with this term here, the 5 sig figs of the percent abundance is limiting me again. So 1, 2, 3, 4, 5. Now that I'm adding the numbers up, I want to consider decimal places. 3 decimal places and 4 decimal places. So we're down to 3 decimal places for that. For the other set of numbers that I had to combine, that had the y variable associated with them, all of the values are going to stand. So because they come from the data. So I can maintain 1, 2, 3, 4, 5 decimal places. 1, 2, 3, 4, 5. Now I have to subtract the number that has 3 decimal places. So I wind up with 3 decimal places here in the numerator. That's going to give me 2 sig figs. On the other value, it is what it is. We're not going to cut off any decimal places there. So we've maintained all 5. Which means at the end of the day, we're just going to have 2 sig figs in our answer. So we can keep the 9 and the 9, and we're going to have to round up. So we can do this one as 0.10, and the other value will be 0.11. So my percent abundances can be reported as 10% and 11%. So not as precise as the original value, but it still all falls into place, because if I do 79 plus 10, I'm at 89%, plus another 11% is gonna give me 100%, and I need to sum up to 100. In addition, I'm gonna do that quick check where I throw everything back into my calculator and make sure I obtain the average atomic mass.